Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Well, you have to go a little way back when plastics were discovered and when plastics came into being as be-all and end-all of our life, pretty much. We store a lot of things in plastics. At that time, plastics were mostly generated from certain chemicals that were polymerized, and these polymeric molecules would not degrade a whole lot. So that's why some of the older plastics remain for a long time. We have done some preliminary experiments, which is going to be published soon. It's under review. So what I can tell you is what we know in general. We have taken some of the common plastic materials that are out there and exposed them to intense UV light and try to see how they would disperse themselves. And they do become microplastics. Now, once it becomes hydrophilic, that's where material can actually get into the environment and also get into the human system itself. Now, the transport of these materials into the environment, whether into the water stream, into the biota, and also into the air, that's the final, that's what our aim is. That's why I got into this research in the first place.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Kalliat Valsaraj. He's the Charles and Hilda Roddy Distinguished Professor of Chemical Engineering at Louisianna State University. We're going to talk about plastic waste in the environment and wastewater, probably cross over into micro and nanoplastics as well. So, Professor Valsaraj, thank you for coming.
Yeah, I'm glad to be able to share some of my research.
Yeah, if you would, tell me about your research. What are you working on right now?
My research area is pretty much in working in the area of environmental transport and transformation of chemicals, mainly having to do with what happens when some of the chemicals are released into either the air, water, soil, and all the environmental media in general. And my current research is mostly on understanding the behavior of microplastics and how they are generated and what happens to it in the environment.
Yeah, I've interviewed a number of scientists on microplastics. Do you know anyone in the field that's trying to model how fast various plastics break down? I know it's not a perfect environment since outside is so complicated, but is anyone in a lab trying to recreate at least some of the conditions under which plastic would degrade and cycling it fast and seeing how long it takes?
Perhaps it's our group that has been doing that work of late. Myself and Professor Bhuvnesh Bharati, I think you have interviewed him earlier. We have been doing some
today, but about different stuff. But
but we have been doing just that, trying to understand how plastics that are generally released to the environment, how they transform into microplastics and where they end up and what their consequences are.
Yeah, because on the one hand, I've heard people saying, plastic bottles can, last for thousands of years in the environment without breaking down. So I just picture a perfect plastic bottle sitting there. But Now that I've been learning about microplastics, that's not the case. But I wonder, how long does the transition really take? And what does it look like?
Well, you have to go a little way back when plastics were discovered and when plastics came into being as be-all and end-all of our life, pretty much. I know we store a lot of things in plastics. At that time, plastics were mostly generated from certain chemicals that were polymerized, and these polymeric molecules would not degrade a whole lot. So that's why some of the older plastics remain for a long time. But over time, most of the chemical manufacturers have gone to other methods of production where they have certain additives inserted into it, which makes the plastic not as long-lived as the earlier ones, but generally do degrade under certain conditions such as irradiation or sunlight-induced transformations. So most of the current plastics do have some of that characteristic, and that's why plastics that end up in the environment generally do degrade over time and convert to or release microplastics from their constituents.
Yeah, I've heard that, if you have a PET bottle, it's not just PET. There's like a witch's brew of thousands of plasticizers and all kinds of other additives to it. So is it the base material that is not degrading? It's the other materials in it, the additives, or is the whole thing degrading? And can you tell?
It's a combination of both. The plasticizers that are introduced into it actually do catalyze certain reactions, and thereby the original backbone of the plastics do degrade over time if they're exposed to sunlight and UV radiation, which makes it a little bit more difficult to understand how they transform in the environment. But they do, yeah. I mean, the plasticizers do help in not only degrading the plastics, but also in maintaining its original intent as inert material.
So what have you discovered about the true lifestyle plastics? What, the various ones, how fast do they degrade, and what does this degradation life cycle look like?
We have done some preliminary experiments, which is going to be published soon. It's under review. So what I can tell you is what we know in general. We have taken some of the common plastic materials that are out there and exposed them to intense UV light and try to see how they would disperse themselves over time into the water as microplastics. It takes anywhere from several hours to many weeks or more sometimes in cases for some of the plastics that we have tested. But there are probably different types of plastics which have half-lives which are quite variable. We don't know all of them because we haven't tested all of them. We have used a few just as test cases.
I mean, I guess I'm picturing like soda bottles sitting in a tank of water, maybe with some sand in the water or turbidity, and you have a light source, and the tank is sloshing around over and over and over and tumbling and stuff like that. And I don't know if that would be a good model to model the breakdown of some of these, but what is your your layout look like? Like what kind of conditions is the plastic in, and what does it look like, and all that?
So what we have done is we have taken some of the plastics, put them, they do float on water, of course, and then we subject them to UV light, that is sunlight, and then look at how those particles actually disperse into the water, because they become denser and they do disperse into the water over time when they become microplastics. So yeah, we have observed them in real life in our laboratory environment.
Ballpark, what is how long does it take? And I know it depends on the material, but ballpark, what's the window of time it takes, what you consider to be a significant amount of microplastics to be shed?
I would say a couple of weeks, a few weeks, they will actually degrade, and you will see some microplastics in the water.
Oh, wow. Okay. What does the original bottle look like, for instance? So the original plastic, does it look like it's leached anything, or does it still look intact? Does it look ragged or in pieces, or what does it look like?
Yes, they do have different characteristics once they're exposed to sunlight, and you will see certainly a different type of image that you could observe from starting from the initial to the final. How different that is, it depends on the plastic. I mean, you will see certain pitting or certain kinds of transformations and change in colors, actually, in some cases. So I don't know exactly how to give an overall characteristic of it, but we do see some changes.
Why are there, if there's pitting, I guess that means there's preferential sites of degradation.
Mm-hmm.
Is that due to imperfections in the plastic molding itself? Or like, if you look at the surface characteristics, can you tell where a plastic is going to wear first? Or is it at certain dimensional changes in the bottle, let's say?
We can't say that. We cannot say that right now. I don't think we have gone to that extent of trying to figure out which point in the plastic or at what location do these degradations occur. We can see general characteristics, but not very specific.
Do you notice that the degradation is happening faster, let's say, near the cap or near where the plastic is bending at sharp angles, or where it's pinched together or thicker or thinner? Do you see any of that?
Well, I think you are mistaken that we don't use actual bottles, but we use pieces of the plastic, not the actual bottle itself. So, I can't tell you where on the bottle will these degradations occur. We are testing this concept that macroplastics, that is macromaterial that you expose to sunlight, will eventually release microplastics, and that's the key.
Well, why not use an actual bottle?
An actual bottle will be useless for us because we won't be able to characterize the actual transformation. We would rather do it in a laboratory environment where a piece of the plastic is used, not the actual bottle.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now, back to the show.
Yeah, but I mean, if you have a monolithic bottle, you have a much smaller amount of surface area than, let's say, a piece of plastic that you'd put into, a lab scenario. And I was going to ask you, too, when stuff breaks off the plastic, how macro is it? And at that point, the surface area to volume ratio would be much higher. So I would think the degradation would massively accelerate once stuff flakes off,
You are probably right in that, but the intent is, nobody has ever shown really that the dispersibility of the microplastics will increase if you expose it to sunlight. And that is the one key aspect that we have been investigating. This is a test case.
What about once the plastic has started leaching, does it accelerate? Do the pits grow faster? Now and again, as more surface area, does the release of microplastics accelerate over time?
Not really. We haven't seen that kind of behavior. We have seen a fairly exponential decay in I would say, a fairly linear increase in the amount of microplastics that are generated. We are still in the process of characterizing the rates.
That's weird. That would seem to suggest that there are definitely site-specific areas where the degradation happens first. And once the materials at that microsite, I guess, deplete, then the degradation slows down because maybe now you don't have as many of those like juicy, sites to degrade.
That is right. That is probably correct because the backbone material, which are essentially polymeric materials, will probably not degrade that much. It may take much longer to degrade those backbones.
So does that suggest that the backbone material is the slowest to degrade? And again, it's the additives, the other chemicals, the plasticizers, et cetera, the stuff for color and all that, the weak points in the structure?
Yes, that is correct. And we do have, what we do is we can characterize what type of functional materials are actually generated in the microplastics over time. And we do see oxidation, actually oxidized materials in the microplastics. So we do not know yet exactly how the overall degradation would occur, but we do know basic tenet of our work has been to show that the macroplastics would eventually give rise to microplastics, and that's been shown.
What's coming off is, I guess, along the boundaries of these added chemicals is where the weak points are. This is just my guess. And when they're coming off, a piece of the backbone is coming with them. So you get a microplastic maybe that has core backbone of the PET, whatever it is, and it still has these, maybe additives on top of it. And then I guess over time, if that exterior coating wears away and you're just left with backbone, but in a very small piece, maybe the degradation stops there or slows dramatically.
That is speculation right now because we don't have evidence to show all of that. We are still in the process of evaluating what the characteristics of these microplastics are with respect to vis-a-vis the original plastic. So you're pretty much speculating what would happen. And yeah, that's a scenario, but I don't know if I can tell you that that is exactly what's happening.
Yeah, no, I understand. It's just pure speculation. You know, armchair microplastic science here, but
that's exactly right.
What have you looked at the surface chemistry and the surface morphology before and after degradation and compare the two? And what do you see if so?
Mostly what we see is, as I said, if you start with a macroplastic that is pretty much hydrophobic, that they do not disperse in the water, over time we see that most of that material that degrades become hydrophilic over time. So they do just get into the water. And that's the transformation that we see from a hydrophobic, mainly hydrophobic plastic, macroplastic, to hydrophilic microplastics.
If you look at the surface of the microplastics that come off, do they have like their own biofilms on them?
No, we're not seeing any biofilms because we don't deal with any bioorganisms in these cases, or even any kind of biofilms. We're using pretty much nascent plastic material, so I don't think there is any biofilm formation that we have seen.
Are you doing this just in like distilled water, or what's the medium of dissolution?
It's distilled water, yes.
As degradation occurs, are you seeing like pH changes or various ions being formed that weren't there before? Like if you looked at the water chemistry?
I don't remember what the student has done with respect to the water chemistry. We were mostly interested in the surface chemistry of these plastics. So we do know that there are changes, and that's why it's becoming hydrophilic. What the characteristics of them are, what the pH of the solution is, I don't remember that the student has done that. Well, you cannot really see a lot of changes in pH. I mean, you have to really release a lot of hydrogen ions to see a huge change in the pH of the water. I don't think that'll be discernible with the kind of solutions that we are using. I mean, you'll probably have to have a lot of microplastics formed in order to observe that.
Well, have you tested, I guess in natural waters, I don't know how much pH variation there is, but are you going to go back and try like slightly basic, slightly acidic, and see if there's dramatic differences in the degradation?
Yeah, that is we have only, as I said, we have been using distilled water. We haven't used natural water and the natural water pH, whether it's seawater or lake water or any other kinds of waters. So that is our overall aim. I mean, this project was an initial test and essentially an NSF grant that just was a 2-year grant, just demonstrating that the transformation from macro to microplastics and what happens to those, and further evaluation will be in another project.
And how much microplastic is generated, maybe per cubic centimeter of plastic volume? Are you able to make that calculation at all?
I don't think we have made that calculation yet. We are mostly interested in demonstrating that it is hydrophilic material and not, we haven't characterized how much plastics are generated.
And what about looking at the, again, morphology profile of the microplastics? Do you get different sizes, different shapes, sharp edges? What does it look like?
We do get different shapes and sizes, certainly. It is yet to be, we have yet to figure out how we can characterize them.
Yeah, and I guess it'd be interesting to see, in the beginning of the degradation, I wonder if you get certain shapes, and then later on in the degradation, if the shapes change, or they further, again, get whittled down, by the action of the water, and like what's the initial size distribution? Are you getting micron pieces first and then submicron pieces later? And, it'd be interesting to see all that.
Yeah, absolutely. That's our intent.
How many different types of plastic have you guys tested so far?
I believe we have used several different types of plastics that are existing. I don't remember exactly how many, but I know that there's been at least 2 or 3 different varieties of plastics that we have worked on.
Are you seeing big differences in the types of plastics, the degradation profiles?
Yes, there are certain significant differences between different types of plastics, made out of different backbones, you obviously will see different degrees of hydrophilic materials that are being generated.
Yeah, I've heard from doing laundry, a lot of fibrous or fiber microplastics will come from there. Mm-hmm. But of the plastics you're working with, like what do the microplastics look like? Are they just like spheroid, or are they star-shaped, or like what kind of shapes are you seeing?
Various different. I have to go back and figure out, I don't remember exactly what type of shapes and sizes we are seeing, but obviously we do see certain types of fibrous materials are generally the ones that you will see first, because mostly these polymeric materials will generate those fibrous compounds. Now, is that all that happens? I don't know whether they will transform further if we subject it to UV light and sunlight over time. We don't know.
Yeah, do a lot of plastics have like a micrograin structure?
Yeah, they do.
Okay, so I guess along these lines, in between the grains, is where the preferential wearing seems to occur. Is that right?
Could be, yes. That all remains. Again, I don't want to speculate on what happens because we haven't looked into it, what transformations occur and how they occur and where it occurs. That is really a significantly longer undertaking because it will require a lot more work.
Okay. So what so far is jumping out at you based on the data you're getting? What you can say, but any interesting things you can point out as to what you've observed so far?
Yeah, the primary thing that I can tell you is that materials that tend to be hydrophobic, that is plastics in general, over time does become hydrophilic, and they do become microplastics. Now, once it becomes hydrophilic, that's where material can actually get into the environment and also get into the human system itself, because that's where these materials will eventually end up in our gut system. You know that there was a very interesting article in National Geographic not too long ago about finding microplastics in the human systems itself. Certain organs in our body do have tendency to accumulate these things over time, and that is really the hydrophilic material that is getting into our system. So human consumption, and it's much like particulate material in the air, which mostly when it becomes micron size and submicron size, we do tend to imbibe them. And the same thing happens plastics and microplastics as well, and nanoplastics in particular. So that's a fairly important conclusion, I think. How does it get into the biota in general? And, whether it is fish or amphibious material, amphibians, or even how does these microplastics enter our system?
Yeah, I would guess that it goes into the body, and if you eat it, the stomach acid probably breaks it up and changes the active site structure and everything. And then again, it's speculation again, but I would think people that have a leaky gut are more likely to have this enter into their bloodstream and into their interstitial tissues and everywhere else than people that don't, but also organs that blood passes through. I guess liver probably would be maybe a main candidate for the accumulation of this stuff, other organs. But do you know from the article like where they were observed preferentially in the body?
I do remember that liver is one of the main organs where it is observed. Now, it has these microplastics eventually has a different consequence as well, and that is they do behave much like endocrine disrupting chemicals. So they do have other public health effects, which some folks are actually investigating that. And I know that there are several papers that I've seen where the effects of microplastics, not on the humans, but at least in mice models, have been understood to show some very interesting characteristics once it enters the biota.
Okay. What future questions are you looking to ask? What's come up recently that now you want to investigate?
Yeah, well, one of the reasons why I got into this is there was a paper in Nature about 3 or 4 years ago which showed that nanoplastics and microplastics are found in environments high up in the Alps where there is no evidence of microplastics being ever used. And the pathway that they envisaged and actually demonstrated was the air pathway. So much of the microplastics that tend to be generated in the water stream or on land tends to disperse in the air and reach these very remote locations, much like DDT and other chemicals, which are non-volatile and not very conducive to transport. Essentially, it does transport to these remote locations. So that was where we started to think about what happens to these plastics. Are they just getting transformed to micron-sized particles and then get transported? And so what we have done shown is that, yes, they do transform. Now, the transport of these materials into the environment, whether into the water stream, into the biota, and also into the air, that's the final, that's what our aim is. That's why I got into this research in the first place.
Okay.
Air transport pathway is yet another important aspect which folks are beginning to understand.
Well, in your test chambers, I guess the plastics in distilled water, but are you seeing any aerosolization? You're agitating the water and sampling the air.
No, we haven't done any of that. That is a long way off. Really, we want to figure out what happens to them in the first place, and then we can think about aerosolization and all of that.
Okay. Well, what other, what other important aspects of this do you want to study? What are you trying to figure out in addition that you think will be very useful?
Well, I think if we can get some veterinary science folks or somebody who is interested in understanding the biota influence, that's where we really want to tie our research with certain mice models and other stuff to figure out, well, where does this end up, and in which organ does this end up, and how does it reach there, and what their consequences are. So there's a larger component of this work, which hopefully will take several years' effort, but that's where we are headed.
Okay. Well, very good. Professor, where can people find out more about your work? Where can they go?
We are about to publish this article. It's actually being reviewed right now. And there was also a review article about microplastics that Bhuvanesh, Professor Bharati had written last year, I think. And that's where you could get some of this idea about colloidal transformations and hydrophilic balance in microplastics. The most recent work, it's under review, and hopefully it'll get published very soon. And that's where you'll be able to get a lot more information on what we are doing.
Very good. Well, Professor Valsaraj, thank you so much for coming on the podcast. I really appreciate it.
Absolutely. Be glad to. And hopefully, if you're ever going to put anything in on your podcast, certainly like to see what you're putting together.
Sure. All right.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.